To demonstrate transfer learning, in this video, I will show how to use the VGG16 convolutional base for, let's say, building a model for the CFAR10 dataset. Now, let me briefly talk about the CFAR10 dataset. CFAR10 is a collection of images that are commonly used to train machine learning models and computer vision algorithms. It is one of the most widely used datasets for machine learning. The dataset contains 60,000 32 by 32 color images in 10 different classes. You can think of this as a different type of MNIST dataset, while MNIST is only digit classification. CFAR10 is image classification, but since datasets like ImageNet are really, really big, CFAR10, on the other hand, is extremely small. The 10 different classes represent these things in the real world, airplane, cars, etc. And there are around 6,000 images in each class. So to download this data set into memory, it's pretty easy. All I have to do is TensorFlow.keras.datasets, import CFAR10, and then do CFAR10.load data. And this gives me the data set in 4 different NumPy arrays: Xtrain, Ytrain, Xtest, and Ytest. So if we visualize this, Xtrain is 50,000 images, 32 by 32 each, color images, and Ytrain is 50,000 labels. So let's randomly plot one of the input images to see how it looks like. So it looks like the 5th training image 4, is the picture of a car. Now say instead I would like to visualize the 6th input image, and here's the 6th input image. This is also a picture of a car, and so on. Now let's convert the data set, that is our labels, into 2 categorical, because so that it's ready for training, we have to convert those into 1-hot encoded output labels. So our 50,000 labels become 50,000 by 10, and our 10,000 test labels become 10,000 by 10. So now we have our data ready to be trained. The first method is to develop our own convolutional neural network. That is, we simply have our input images of shape 32 by 32 by 3, and then I can have a first convolutional layer with 16 filters in it, and then I can have second convolutional layer with 4 filters in it, and then I can flatten it, add dense layers, and in this way, this is just a tiny model, but we can build any model that we want and then train it. So let's build this model, and so our model is ready, only 32,000 parameters, and then say I would like to train it, right? So let's say I set the number of epochs to only 4, and batch size to something slightly very higher so that I can get results much more quickly. And we notice that the validation accuracy is 39%, 43%, and 43%, and so on, right? So now I can also plot the history and like the learning curves and see how the training went. So that was the first method that we all know so far. Now let's look at the second method, that is how to use the VGG16 convolutional base. So to do this, we have to first download the VGG16 convolutional base. To do this, I can do TensorFlow.keras.applications, import VGG16, and then VGG16, give me the VGG16 convolutional base. The weights for this model must be trained using ImageNet. Keras already comes packaged with this. And then I also did include top equals false. What this means is I'm only requesting the convolutional base part of the model pre-trained. And I'm also asking the input shape to be reshaped to 32 by 32 by 3, so that now I can use the CFAR10 dataset, because otherwise VGG16 by default is not trained for 32 by 32 3 input. Now the next thing I would like to do is visualize this conv base summary to see how it looks like. And here it is. It accepts an input of 32 by 32 by 3. This is the input it accepts. And then what it produces as output is 1 by 1 by 512, a very deep representation of the input. So there's no dense layer here. This is all convolutional layers and max pooling layers. So the next thing that we would like to do is take our inputs, that is our X test and X train as input, and pass them through the convolutional base and obtain the representations of our input that would be produced from the VGG16 base. So let's run this. And what this gives us in these two NumPy arrays, that is the XTest VGG output and XTrain VGG output, is the different kind of representations of our input images, which is learned by the convolutional base of VGG16. Now, since these are latent representations, the number of channels for each of these is, the output is going to be 1 by 1 by 512 for each image. So in the test data set, what we have is 10,000 images, and then these 10,000 images each are represented as 1 by 1 by 512 volume, and the train images 50,000 are represented by 1 by 1 by 512 volume. So for each image, now we have these 512 numbers, or this 1 by 1 by 512 NumPy array representing what the input image means. Now the next thing that we would like to do is reshape our input, or in a way actually flatten these representations so that they can be fed to a dense layer. So here all that we are doing is we are taking the XTest VGG output and we are reshaping them to, so these are 10,000 images, so we are keeping the number of images same, but then now this is effectively basically only 512, so I can either have 1 by 1 by 512 or simply flatten it out and only put 512. Regardless, it's the same thing, and we're simply flattening these representations so that these become like, each image now becomes like a vector that can be fed to a deep learning model. So now if you look at this shape, this becomes 10,000 by 512 and 50,000 by 512. So now our input images, in a way, they become like a table or a vector or a row in a tabular data. So now we can simply build a sequential model with dense layers. Let's say I would like to add 256 neurons in the first layer, and then I would like to add a dropout of with 0.5, and then finally dense layer that predicts 10 values, right? And then the input dimension for my for this model will be 512 values, and this 1 by 1 by 512 is basically 512. And then I can do model.compile and then run model.fit. So this time, let's build this model and then train slightly longer, say for example 6, and let's actually do 32 epochs, and then let's train this model. So what we have done here is taken these representations captured by the VGG16 base, and then we are feeding those as inputs to our new neural network, which is simply all only the classifier layer or the dense layer part of our network. Remember, our entire network is actually much bigger because it includes the VGG16 base as well. So we see that the accuracy on the validation set is around 60% now. On the training data set, the accuracy is 61.2% and so on. And maybe this is actually what we get right now. We can maybe further choose a slightly different convolutional base, or even do fine-tuning to further improve the accuracy. That is, unfreeze some of the convolutional layers in the VGG16 network to further raise the accuracy on the validation set. So we have the training complete. Of course, you can incorporate overlay stopping and many of the stuff to obtain higher accuracy. And then here's the model accuracy, or the learning curve showing the training accuracy and the validation accuracy over epochs.